So we start our discussion with resolution of vectors. Now resolution of vectors, it simply means splitting a vector into different parts. So resolution simply means splitting a vector into many parts, and those parts in which a vector is splitted will be called as the components of the vector. Now suppose there is a vector A, and suppose this has been split into many parts, and those splitted parts are suppose some p vector, m vector, n vector, and so on. A vector can be split into many parts, and those parts are called as the components of the vector. So p vector, m vector, and n vector are called as components of the vector A. Alternatively, you can say that p vector, m vector, and n vector, their resultant is A vector. So A vector will be called as the resultant of p vector, m vector, and n vector. Apparently, you might think that the process of resolution of vectors is just opposite to the process of addition of vectors. So in addition of vectors, we found the resultant of a given set of vectors. In resolution, we divide or we split a vector into different parts. But when two vectors are added, it produces only one resultant. Whereas in resolution of vectors, you can obtain different sets of components. That means p vector can be again further split into two or more components. Similar with the case of m vector and n vector. So it is not exactly the opposite process of addition, but it apparently seems so. So what we are trying to do is, we are trying to split a vector into different parts. For the time being, I am trying to demonstrate how a vector is split into two parts. So for that, let me draw a diagram. So suppose I have a vector A, or let me denote it as R vector. Suppose the starting point of the vector is O and the finishing point is A. So this is called as OA vector. Let me call it as R vector. Suppose the line segment OA makes an angle alpha with another line. Suppose that line is called as OM. That means the vector R is making an angle alpha with a predefined direction or a predefined line segment, that is OM. And suppose it makes an angle beta with another direction or another predefined line segment, suppose that is ON. And that angle is suppose beta. So let me complete the parallelogram. So this dotted line, suppose this is called as AB. This dotted line is parallel to ON, and this dotted line is parallel to OM, suppose. This dotted line is parallel to OM, and this dotted line AB is parallel to OM. Let me name this dotted line as AC. So AC is parallel to OM and AB is parallel to OM. That means we have a parallelogram OBAC. Now in that parallelogram, we can definitely apply the parallelogram law of vector addition. Suppose I call OB vector as A vector and BA vector as suppose B vector. This remains the dotted line just to indicate as a vector with the direction with the arrow BA. So what I have is OA vector is R vector, OB vector is A vector, and BA vector is B vector. So that means we have the parallelogram OBAC. So in this parallelogram OBAC, we can apply the parallelogram law of vector addition, and we can write R vector is A vector plus B vector. So we have resolved R vector into two parts. One is A vector and one is B vector. Now if this angle is alpha, this angle is alpha plus beta. So this angle is obviously alpha plus beta because BA is parallel to OC. And as we know that angle in a straight line is 180 degree. 180 degree can be written as pi radians. So this angle, that is angle ABO, is obviously pi minus alpha plus beta. This is pi minus alpha plus beta. So now a popular principle in trigonometry is the sine rule. If we have a triangle, suppose triangle ABC, and suppose this is angle A, this is angle B, and this is angle C, and the sides opposite to the vertex A is suppose small a, side opposite to vertex B is suppose small b, and the side opposite to vertex C is suppose, this is capital C, the vertex are all denoted by capital letters, and this is suppose small c. So this rule is very popular in trigonometry, that is A upon sine of the angle A is equal to B upon sine of the angle B. That means the side by the angle facing it is in proportion. Small c divided by angle of sine of angle C. So this is called as a sine rule that I will apply here. So if I apply in this triangle OAB, if I apply the same rule, what I will get is if I take this angle, this is angle OAB, so I have to take this side. So if I write OB by sine angle OAB is equal to, if I take this side AB, angle opposite to this is alpha, I will write sine alpha is equal to, if I take OA, I have to consider this angle, that is pi minus alpha plus beta, I will write sine of pi minus alpha plus beta. So now you can see that OB means the magnitude of A vector. So OB means A by sine of angle OAB. Now instead of writing sine angle OAB, this angle is obviously beta because you see that OC is parallel to AB. So this angle beta is alternate to this one. So these are both equal. So instead of writing OAB, I can write beta. So this is sine beta is equal to AB. AB is the magnitude of B vector. So I can write B by sine alpha. And OA is the magnitude of R vector, that is R. And remember, sine pi minus theta is sine theta. So sine of pi minus alpha plus beta is obviously sine alpha plus beta. Hence, the components A and B could be determined from this equation. So if I omit this and continue what I get is R equal to, or if we want to move A and B, so A equal to R into sine beta plus sine of R sine beta by sine of alpha plus beta, and B another component, that is R sine alpha will be multiplied with R by sine of alpha plus beta. So we have determined the magnitude of the components of R vector. So you see that R vector was equal to A vector plus B vector. It was split into two parts, and the magnitude of the two parts are R sine beta by sine of alpha plus beta and R sine alpha by sine of alpha plus beta. A special case of this, what we use frequently, is when alpha plus beta is 90 degree. If alpha plus beta is 90 degree, then we call this process of resolution as resolution into rectangular components. I hope you have noted this. So what I am saying is that if alpha plus beta is 90 degree, then this process of resolution will be called as resolution into rectangular components or orthogonal components. If alpha plus beta is 90 degree, then what you will have is, you will have OM parallel to OM. Sorry, they will be mutually perpendicular. OM will be perpendicular to OM. Then the process of resolution will be called as resolution into rectangular or orthogonal components, because orthogonality means perpendicularity. So the components will be now called as the orthogonal components, because we have tried to resolve R vector into two mutually perpendicular directions. So if this happens, then you can say A equal to R sine, instead of beta, what you can write sine 90 minus alpha, sine alpha plus beta. Alpha plus beta is 90 degree, so sine 90 is 1, so this becomes just R sine 90 minus alpha, and R sine 90 minus alpha means R cos alpha. So this is what we get. And B equal to, instead of sine alpha, you can write sine 90 minus beta, or you can leave it as sine alpha. And B equal to R sine alpha, just because sine alpha plus beta is sine 90 is 1. So these are the two components you get. A is R cos alpha and B is R sine alpha. That means you just know this angle because the directions are mutually perpendicular. So if you know alpha, you can definitely calculate beta. Actually, there is no need of calculating beta further. You can say A is R cos alpha and B is R sine alpha. As I have said that if the lines OM and ON are mutually perpendicular, then the components will be called as rectangular or orthogonal components. So you definitely know that in the coordinate system there are two axes which are mutually perpendicular to each other. Obviously they are the x-axis and y-axis. So whenever we are trying to represent a rectangular or orthogonal component, it is preferable to take the x and y axis instead of the directions or the names OM and ON. So suppose this is the y axis and this is the x axis, and let the vector R that was denoted as OA. O refers to the origin of the coordinate system. This OA vector is R vector. And in a similar manner, we draw perpendiculars from the point A on the x-axis. This is the point B, that is the perpendicular, and we draw perpendicular on the y-axis. This point is called as the point N. And now this is your A vector and this is your B vector. So now you can say that R vector is A vector plus B vector by applying either the triangle law or the parallelogram law, and then if this angle is alpha, then you can say A is R cos alpha and B is R sin alpha, and this component is called as the horizontal component. The horizontal component, and this component B is called as the vertical component, because the x-axis is generally considered as the horizontal axis and the y-axis is considered as the vertical axis. So inclination with the horizontal direction is called as the horizontal component, and inclination with the vertical direction is called as the vertical component. So generally you can say that the component which refers or is connected with the cosine of the angle of inclination, it is called as the horizontal component, and the component which is connected to the sine of the angle of inclination, it is called as the vertical component, because not necessarily the x-axis and y-axis will be always horizontal or vertical. You can choose the directions of axis as per requirement. Suppose instead of the horizontal direction, suppose this was the x direction and this was the y direction and this was the vector r, and if this is alpha, then obviously this is your A, which is r cos alpha, and this is your B, which is r sin alpha. One cannot say that this remains horizontal again, because this is diagrammatically not the horizontal actually, neither this is the vertical. So horizontal or vertical, these terms are preferably used whenever the given axis is horizontal, with which the angle of inclination is alpha, and the given axis is vertical, with which the angle of inclination is obviously 90 minus alpha. So this will be obviously 90. 90 is pi by 2 radians. So this is 90 minus alpha or pi by 2 minus alpha. But whenever we solve numericals, we usually say that the component connected to the cosine of the angle of inclination is horizontal, and the component connected to the sine of the angle of inclination is vertical. Now, while discussing unit vectors, I told that the x direction, the positive direction of the x-axis, is denoted by a unit vector which is called as the I vector or the I hat or I cap, and the vertical direction or the direction of the y-axis is indicated by another unit vector which is called as j hat. And so following this, you can say r vector is A vector plus B vector. Because A is a vector, its magnitude is r cos alpha. So instead of A vector, you can write its magnitude A into the unit vector along its direction, that is I hat, plus instead of B vector, we can write its magnitude modulus of B into the unit vector along its direction. See that B vector is along the y direction because they are parallel. So this can be written as j hat. So A vector is modulus of A I hat and B vector is modulus of B j hat. Now what is modulus of B? This is modulus of A is simply A and modulus of B is simply B. That means the magnitude, and A is r cos alpha. So this is r cos alpha I hat plus r sin alpha j hat. Now if the coordinates of the point A and Y are x and y respectively, then obviously this is x and this is your y. So instead of r cos alpha, we can write x. So this is x I hat plus y j hat. Instead of r sin alpha, you can write y, because this is your r sin alpha and this is y indeed. So if the coordinates of any point is given, you can always define a vector which will be called as the position vector of that point. So as per this diagram, I can say r vector is the position vector of the point A with coordinates x and y. And then we can write the position vector r vector. The position vector means its origin is at the origin of the coordinate system. Whenever we write position vector or whenever we indicate position vector, it is with respect to the origin of the coordinate system. So here the coordinate system has its origin at O. So the vector r will start from this point and it will end at the given point whose coordinates have been mentioned. So this will be r I hat plus y j hat. So in general, you can say for any point having coordinates x and y, its position vector is x I hat plus y j hat. And obviously your x is r cos alpha. That's why it is frequently called the horizontal component, and y is obviously r sin alpha, and so it is called as the vertical component. For any point, suppose 3, 4 in the coordinate plane, its position vector is 3 I hat plus 4 j hat. So for any point on the coordinate plane or any point on a plane, you can always associate a position vector, and not necessarily in a plane. If we have 3 axes, suppose the x-axis, y-axis and z-axis, you can also associate a position vector with any point in space also. We continue our discussion of resolution with respect to the 3-dimensional space. So suppose you have 3 set of axes, the y-axis, the z-axis and the x-axis, and the origin is at the point O, and I have constructed a cube A, B, C, D, E, F and P. So suppose the point P is a point in space and it has the coordinates x, y and z, and so the origin has definitely the coordinates 0, 0, 0. The point A, which lies on the x-axis, should have components or should have coordinates x, 0, 0. The point on the y-axis should have coordinates 0, y, 0, and the point on the z-axis, that is the point D, should have coordinates 0, 0, z. So if you remember, the directions of y, x and z axis are all represented by unit vectors. The direction of x axis is represented by the unit vector I hat. The direction of y axis is represented by j hat, and the direction of z axis is represented by k hat. Now, as I have told, whether in space or in plane, any point with its given coordinates can be represented by a position vector starting from the origin. So if P is a point in space having these coordinates, we can always have a position vector, OP vector, starting from the origin O and ending at that particular point. So this is your OP vector, and let me call it as R vector. So here OP vector is your R vector. Now, if you see the polygon OABP, in this polygon OABP, if we apply polygon law of vector addition, then you can write this OA vector plus AB vector plus AB vector plus BP vector is obviously equal to OP vector. So OP vector is R vector, and what is OA? OA is obviously x, and for the vector we use the direction. X is the magnitude of OA and its direction is along x-axis, so this is x I hat. AB, it is parallel to OC, and because OC is y, so AB is also y, so its magnitude is y and its direction is along y direction, so it is j hat. BP, BP is parallel to OE, BP is parallel to OE, OE is z, so BP is also z, and its direction is along z axis, so this will be z k hat. So thus you can say that with respect to any point having coordinates x, y, z in space, you can have a position vector x I hat plus y j hat plus z k hat. Now if you want to find the magnitude of this position vector, so if you refer to the cuboid again, we can easily find what is the magnitude of r vector or simply r. R vector or magnitude of r are same actually. So if you can properly realize the properties of the cuboid, you can just easily say that OP square is OA square plus OC square plus OE square. You can easily say that OP square is equal to OA square plus OC square plus OE square. And so because OP is r, so this r square is OA square. What is OA? OA is x, x square plus OC square. OC is y, so this is y square plus OE is z, so this is z square. So that implies r is equal to the square root of x square plus y square plus z square. So this is the magnitude of the position vector, and this is indeed the position vector. Similarly, in two dimension, for any point p x comma y, its position vector is x I hat plus y j hat, and its magnitude is root over x square plus y square. So we just omit this z in two dimension. Z is taken to be 0 because there is no z axis. So if with respect to the plane of the board, this is the x axis and this is the y axis, you can always find any point having coordinates x and y, and its magnitude will be square root of x square plus y square. So three dimension is just the generalization of this. Now, as we can say that there is a position vector with respect to any point in space or in plane, we can also associate the direction of the position vector by another unit vector. So suppose we have a unit vector along this direction, along r vector, along the direction of r vector, we have a unit vector which is called as r hat, suppose. That means now I can write r vector is modulus of r vector into the unit vector along its direction. And so this r hat will become r vector by its modulus. And so from here, replacing r vector and its modulus as this one, we can find the unit vector along the position vector. So the unit vector along the position vector will be simply r hat, which is x I hat plus y j hat plus z k hat divided by its modulus, that is x square plus y square plus z square square root. And in two dimension, similarly you can say in two dimensions r hat will be x I hat plus y j hat by root over x square plus y square. So now it becomes very easy to find the position vector, the unit vector along the position vector. So if the angle of inclination of the position vector with the respective axis we know, then we can use the properties of a cuboid in 3 dimension and the properties of a rectangle in 2 dimension to find the angle of inclination, and those angle of inclinations are called as the direction cosines. So if r vector is inclined at angles alpha, beta, gamma respectively with x-axis, y-axis and z-axis, then we can say cos alpha is equal to x by r, or as per this diagram you can say cos alpha is your OA divided by OP, which is x by r. Cos beta is OC divided by OP, which is y by r, and cos gamma is OE divided by OP, which is z by r. Now this cos alpha, cos beta and cos gamma, they are called as the direction cosines of the position vector. So cos alpha, cos beta and cos gamma, they are called as the direction cosines. All these 3, they are called as direction cosines. And if you find cos square alpha, cos square beta and cos square gamma, you will see that their sum is 1. You can check cos square alpha plus cos square beta plus cos square gamma. This will be x square by y square, x square by r square plus y square by r square plus z square by r square. That is x square plus y square plus z square by r square is obviously x square plus y square plus z square, because if you remember, r was square root of x square plus y square plus z square, and if you square it, the square root is eliminated, so this is 1. So the sum of the squares of the direction cosines is 1. So hence, in order to know the direction of the vector, the angles alpha, beta and gamma that the vector makes with the x-axis, y-axis and z-axis respectively can be determined using these equations, and thereby you can also find the position of the vector. If you know the coordinates, then only you know the position, and by knowing the coordinates you can also calculate the angle that the vector makes with the x-axis, y-axis and z-axis respectively. So in 2 dimension it is very easy to visualize. In 2 dimension, if this is the vector, r vector, and this is your y-axis and x-axis respectively, then obviously this is perpendicular. R cos alpha will be equal to this one, which is x, because x is r cos alpha, as I have already told. So this is x. So you can say cos alpha is x by r, and if you know that it makes an angle beta with y-axis, you can say this is your y, which is r cos beta. This is r cos beta, and if it is r cos beta, then you can say that cos beta is y by r. So it is very easy to realize in 2 dimension, but in 3 dimension also you have to just extend these properties. So now obviously this is x is r cos alpha, provided this angle is alpha, and if this angle is beta, then this is y, which is r cos beta. So from here you can easily see that your x is r cos alpha means cos alpha is x by r, and y is r cos beta means cos beta is y by r. So it is very easy to realize in the case of 2 dimensions, but in 3 dimension you have to extend this realization and project it onto the surface of a cube or cuboid and try to understand it. So now we will learn product of vectors. So whenever we consider product of vectors, it is obviously of 2 types. One is called as the dot product of 2 vectors, and another is popularly called as the cross product of 2 vectors. Now, in case of dot product, the dot product of 2 vectors is a scalar. Dot product of 2 vectors is a scalar, whereas the cross product of 2 vectors is a vector. Is a vector. Now in vector algebra, 2 vectors, if they are multiplied, they can produce a scalar, and if 2 vectors are multiplied, they can produce a vector also. Also, it is possible that if we multiply a scalar with a vector, we will get another vector. So, if a scalar is multiplied with a vector, if a scalar, suppose that scalar is, say, m, is multiplied with any vector, suppose that vector is a vector, then the product is a vector. And the product is a vector, which will be obviously m times the vector a. Now whenever we multiply a scalar with a vector, its magnitude gets multiplied. So if there is a positive m and we multiply with a vector a, then the magnitude of the vector is increased by m times. But if it is multiplied with a negative scalar, suppose m is negative, then also its magnitude is multiplied m times, but its direction becomes opposite. So if a scalar is positive, then the direction of the vector remains unaltered, but if the scalar is negative, then the direction of the vector becomes opposite to the original value. So let us now focus our discussion on dot product of 2 vectors. So dot product of 2 vectors will produce a scalar, and suppose there are 2 vectors, say a vector and b vector, a vector and b vector. Their dot product will be denoted as a vector dot b vector. The dot product of these 2 vectors will be denoted as a vector dot b vector, and it is defined as the product of the magnitudes of these vectors into the cosine of the angle theta between them, where theta is the angle between a vector and b vector. I repeat, theta is the angle between a vector and b vector. So now you can write a vector dot b vector is equal to ab cos theta, because magnitude or modulus of a vector is a itself, and similar is the case with that of b. So this will be the definition of dot product. But why do we need dot product at all? Now the dot product is calculated to find the projection of one vector along the direction of another vector. So suppose this is a vector and this is b vector. So if I draw a perpendicular from a vector on b vector, the angle between a vector and b vector is suppose theta, then this portion of a vector which will get inclined with b vector. That means if you are rotating a vector by an angle theta along b vector, that portion of a vector that will align itself with b vector is a cos theta. Similarly, if you draw a perpendicular from B on A, we will also get the projection of B vector on A vector. That means if you are rotating B vector by an angle theta along A vector, the portion of B vector that will align itself with A vector is B cos theta. So, dot product of two vectors is either the projection of one vector along the direction of another vector. So, this can be written as a vector dot b vector. Now it can be written as a cos theta times of b, which means a cos theta is the projection of a along b or component of a along b. A cos theta means projection of a vector along b vector, or you can say it is the component of a vector along b vector. Similarly, a vector dot b vector could have been written as a vector dot b vector is a times of b cos theta. What is b cos theta? B cos theta is the projection of b vector along a vector, or you can say b cos theta is the component of b vector along a vector. So that is the significance of finding the dot product. We are trying to rotate a vector along the direction of another vector and try to take its component along the given vector. So whether we rotate a vector along b vector or b vector along a vector, we actually perform the dot product of a vector. So on a similar basis, now we can define some important properties regarding dot product. So as you see that the dot product of two vectors is a scalar. So then a vector dot b vector, which is ab cos theta, and b vector dot a vector is ba cos theta. As in the case of scalars, a into b is b into a. So obviously you can say that a vector dot b vector is b vector dot a vector, and this property is called as the property of commutativity. That means you can say that dot product of two vectors is commutative, just like addition of two vectors is commutative. Whenever we write a vector plus b vector, we get b vector plus a vector. So vector addition is commutative and dot product of two vectors is also commutative. So suppose now we find a dot product of a vector with itself. What happens? A vector dot a vector. You will always get the magnitude square of that given vector. Why? Because if a vector is taken, if the dot product of a vector is taken with itself, obviously the angle between them is 0. Because if the same vector is taken twice, the angle between them is 0. A vector and a vector means two vectors along the same directions having same magnitude. So the angle between them is 0. That is, you can say a vector dot a vector is modulus of a into cos 0. And cos 0 is obviously 1. So this is a into 1. So that is a square. So a dot a is a square. Now suppose there are two vectors, a vector and b vector, and they are mutually perpendicular to each other. If a vector is perpendicular to b vector, obviously the angle theta between them is 90 degree, and therefore you can write a vector dot b vector is modulus a modulus b into the cosine of the angle 90 degree between them. Because cos 90 is 0, so a vector dot b vector will be 0. So you can say that this is the condition of perpendicularity of two vectors or orthogonality of two vectors. So you can say that two vectors are perpendicular if their dot product is 0, or two vectors are orthogonal if their dot product is 0. So this is a condition that can be tested while testing the perpendicularity of two vectors. So if a dot b is 0, you can say if A dot B is 0, then A vector is necessarily perpendicular to B vector. This is the condition of perpendicularity of two vectors. Now, using dot product, you can also find the angle of inclination between the vectors. So, suppose you know that the angle between two vectors is theta. A vector dot B vector is AB cos theta. Then from here you can find cos theta as A vector dot B vector by the product of their magnitude. So this might be used to calculate the angle between two vectors. Now, if you remember, the unit vectors along the x, y and z axis, then they were I hat, j hat and k hat. So suppose this is the x axis, this is the y axis and z axis. Unit vector along positive x axis is I hat, unit vector along positive y axis is j hat, and that along z axis is k hat. So simply, what will I hat dot I hat produce? I hat dot I hat will produce 1. Why? Because modulus of I hat is 1, it is a unit vector, and angle between the same direction is 0. So I hat dot I hat is 1. Similarly, j hat dot j hat is 1 and k hat dot k hat is also 1. Because magnitude of unit vector is 1 and the cosine of the angle between same vectors is 0, so cos 0 is 1. So now, as you know that the directions are mutually perpendicular, so you can say that I hat dot j hat is 0, j hat dot k hat is 0, k hat dot I hat is 0, and so on. So this can be applied whenever we are trying to express a vector in component form. Suppose we have a vector expressed as its component form. Just as we expressed a position vector in component form, we can also express any vector in its component form. Let me say that a vector is ax I hat. This is the x component, this is the y component, and this is the z component. Similarly, there is vector b vector, which is x component is bx, y component is by, and z component is bz. So what happens if we take the dot product of these two vectors? So in component form, you can say that a vector dot b vector. So you see that this entire is taken dot product with this entire. So whenever I dot I occurs, you will get 1, and I dot j or I dot k will produce 0. So ax bx you will get. Now ay j hat dot product with this, j hat dot I hat is 0, j hat dot j hat is 1, and j hat dot k hat is 0. So you just get ay by. Similarly, az k hat taking dot product with all these three, az bx, it will become 0 because k hat dot I hat is 0, k hat dot j hat is 0, and k hat dot k hat is 1. So you get az bz only. So this is very easy way of representing the dot product of two vectors when the vectors are given in component form. Now, if you want to find the modulus of the magnitude of the vector, remember what I have done in the case of position vector. It is equal to the square root of s component square plus y component square plus z component square. Similarly, you can say for the magnitude of b vector will be bx component square plus y component square plus z component square. Now if you know that angle between a vector and b vector is theta, so cos theta is a dot b by ab, as I have already defined. So this cos theta will become a dot b is now this one, ax bx plus AY BY plus AZ BZ, and therefore if I divide with the magnitude, this I will get as root over AX square plus AY square plus AZ square into BX square plus BY square plus BZ square. So now you can find the angle between two vectors whenever they are expressed in component form. Now, many physical quantities are actually expressed as dot product. For example, you probably know that work is the dot product of the force vector and the displacement vector. You also probably know that power is the dot product of force vector and velocity vector. So these are two popular physical quantities which are expressed as the dot product of two other physical quantities. Work is a scalar and power is also a scalar. And you see that force and displacement are dot product, force and velocity are also, force and displacement are vectors, force and velocity are also vectors. But the dot product of these two vectors have produced a scalar. Work and power are both scalars. So we can demonstrate the utility of dot product by several examples. Suppose we take two examples. The first example is you have to find the angle between these two vectors. The first vector is I hat plus j hat and the other vector is I hat minus k hat. So let me assume that some A vector is I hat plus j hat and B vector is I hat minus k hat. So what is A dot B? A dot B is equal to the product of the magnitudes and their sum. The product of the components and their sum. So here you see I hat means x component. So here x component is 1. In this case also x component is 1. So 1 into 1, that is 1. Plus, take the y component. In this case there is a y component j hat, but in this case there is no j hat. So there you can say 0 j hat. So this is 1 into j hat plus 0 into j hat. Now with respect to k hat, there is no k hat here, but there is one k hat here. So it is 0 k hat and here it is minus k hat, so magnitude is minus 1. I mean the component value is minus 1. So what you get? A vector dot B vector is equal to 1 into 1, 1. Obviously this is 1. This is 0 and this is 0. So A dot B is 1. And what is the magnitude of A vector? So this will be equal to root over 1 square plus 1 square. There is no k, so that is 0 square. So this is root 2. Similarly, what is B? Here you see there is 1 square. There is no y component and there is a x component, z component, that is minus 1 square. That is obviously plus 1 and again you get root 2. So what is the cosine of the angle between them? By definition, cos theta is A dot B by modulus A modulus B. Now A dot B is 1 and modulus A is root 2 and modulus B is also root 2. So this is half. So cos theta is half. What means? It means that the angle theta between them is 60 degree. Because cos theta is half, the angle theta between them is 60 degree. Now the next question is you have to find n such that the vector A vector, which is 2i hat plus 4j hat minus nk hat, is perpendicular to B vector, that is 3i hat minus 4j hat plus 2k hat. Because the vectors are perpendicular, so obviously you can say the dot product is 0. Because you know that the condition of perpendicularity or orthogonality is that the dot products of the given vectors is 0. So since A is perpendicular to B, A dot B is 0. So A dot B in component form you can now find. This is 2 into 3. plus 4 into minus 4 plus minus n into 2, that will be 0. So this is 6 minus 16 minus 2n equal to 0, which means that minus 10 equal to 2n, which means that n is minus 5.